Okay. Shannon channel capacity. C in bits per second is equal to bandwidth log base 2, 1 plus the carrier to noise ratio. I think we talked about this formula before. It comes from information theory. It basically says that if I have a certain signal to noise ratio and a certain amount of bandwidth, in an additive white Gaussian noise, you can show through information theory that this formula predicts the maximum number of bits per second that you can send through the channel and still get reliable communications to an arbitrarily reliably designed level. You won't make any bit errors. Now, what is this value for binary phase shift keying? In other words, what value does the Shannon channel capacity theorem predict I need to have an SNR in order to transmit binary phase shift keying? Well, in binary phase shift keying, my bit rate is R sub B. And it turns out that the RF bandwidth that I need to support that is R sub B. So I got 1 equals log 2 of this stuff. I raised 2 to both sides of that equation. 2 is equal to 1 plus C over N. Keep in mind this is a formula in the linear scale, so solving for C over N, I need a signal-to-noise ratio or carrier-to-noise ratio of 1 in the linear scale, 0 dB. If I have that, information theory predicts that I should be able to send bits perfectly using binary phase shift keying. That's actually kind of amazing if you think about it, right? The same signal power as I have noise power. 2 competing signals of the same power. One has information, one doesn't. I can perfectly decode the bits. In theory, it doesn't tell you how to do it, but in theory, I should be able to perfectly decode the bits. Now, I just taught you how to calculate the bit error rate for this channel. If I have a binary phase shift keying signal with signal-to-noise ratio of 1, I take the square root of 1 times 2, looking up my formula that floated up to the top there. And if I evaluate the Q function at square root of 2, I get about 0.1. So now there should be some cognitive dissonance registering in our minds. Professor Durgan is telling you 2 different things. He says at a signal-noise ratio of 0 dB, you should be able to send BPSK perfectly. We just looked at uncoded BPSK, and we said that if you transmit a BPSK signal at signal-to-noise ratio of 1, and you just do a raw detection scheme on it, you will get 10% of your bits wrong. That is a useless digital communications channel. So we went from perfect to useless. What's going on? What are we missing? What we're missing is the concept of forward error correction coding, which is used in most digital links nowadays, all but the lower rate, usually. For some forms of wireless networking, don't bother with it. I don't think Bluetooth bothers with coding. But any real serious radio link, including the ones on your project, will likely involve forward error correction coding. And this is how you span the gap between what Shannon says is possible and what uncoded systems typically do, which is pretty lousy. The principle is actually very simple, the idea behind it. Okay. I'm going to put a digital message on the board. It's going to be a brain teaser. Okay, would anybody care to tell me what my message says? Anyone? Oh, you didn't even go here, Evan, and you're volunteering. Go ahead.
I'm guessing it says, I hope you beat the dog. No?
Yes, you're right. That's exactly what it says. I've made errors in this, though. I've made errors in this. By what manner of magic did you work to pull out that signal? How did you do that? I mean, it's not like any digital sequence that I can recognize. I've clearly made some errors because it's not decoding properly up here. How is it that missing pieces of information, he was able to reconstruct the actual message? Of course, we all know the answer. It's actually kind of hard to articulate sometimes, but we all know the answer, right? Your minds, being the great pattern recognition things that they are, snapped to the closest reasonable message in English. You can think of English as a very, very complicated and sometimes ridiculous form of digital encoding. And of all the letter combinations out there, only a tiny, tiny subset of them are permissible based on the English code book. So he found the path through the English code book that led to the closest Hamming distance, probably, to this actual message. With 3 changes, looking at the entirety of the meaning of the sentence, with just making a minimum of 3 changes in the proper context of Georgia Tech English, he was able to snap to the realistic meaning. And this is exactly the principle behind forward error correction coding. I'm going to add redundancy, a bunch of useless articles and spaces that help you read it, and a bunch of vowel combinations that are always going to occur frequently, and et cetera, et cetera. I'm going to add all this redundancy to the way that I encode the message so that if you do make an error, you can actually detect it and, even more importantly, recover it by snapping to the most realistic value or the most reasonable value inside the code book, the one with the least distance, the one with the least changes. But you really need to look at the whole sentence to figure that out. If you understand that analogy, you understand everything there is to know about coding theory. It's just a matter of working out the details from here on out. So there are 2 types of codes that are employed. The first I'll talk about are block codes. Block codes are usually set up like this. I have something called a coded bit stream, C. Think of it as a vector of points. A data vector, vector of 1s and 0s that represent my data points, and a matrix G, which is my generator matrix. I'm going to give you an example of this. So here's my data, 1, 0, 1. And I think several minutes before class, several years ago, I made up this code. I'm going to call it the Durgan code, the Durgan block code. Don't ever use this in a communication system. It has not been optimized. It's only been optimized for ease of instructor illustration, which unfortunately is not the same as bit rate or reliability in a comm link. So here's what I'm going to do. My generator matrix, because I'm always going to wind up with more bits than I started out with, I'm going to make a 6 by 3 generator matrix. And it's going to look like this. And I'm going to multiply this into my matrix. What does that give me? Okay, let me start. I'll give you the answer down here so you don't have to move the camera here. So first 3 rows are the identity matrix. So when I do my multiplication, I get 1 times 1 plus a bunch of zeros. a bunch of zeros. I dot this into here. I get 1 times 0, 0 times 0, 1 times 1. So I did get the same bits to start with. And then I get 3 redundant bits. Dot this into here. 1 times 1 is 1, plus 0 times 0, plus 1 times 1. What is 1 plus 1 in binary? Well, it's 0. You throw away the most significant bit, and you just look at the remainder there. The last significant bit is what you keep. So that would be 0. 1 times 0, 0 times 1, 1 times 1, that's 1. 1 times 1, that's 0. So I get this coded bit. Coded bit. I would call this a rate 3/6 block code. Now, I transmit these 6 bits. And I transmit these 6 bits, receiving in error the following bit. So I receive these 6 bits at my receiver, and there are always 2 levels of error handling in a communication system. There's error detection, which I can clearly do here because it turns out that this set of 6 bits is impossible to generate with any 3 bits in this particular generator matrix. It doesn't exist in code space. And so I automatically know I have made an error. There are other ways to do error detections. You've probably seen things like CRC, cyclical redundancy checks, or parity bits, where you just exclusive OR all the bits together and say, is it 1 or is it 0? If I get one of the bits wrong, hey, I flipped a bit. And I can use my parity check to verify that I sent a bit in error. But we're after bigger game. We want to be able to fix the error. And the way to do that is to look through the code book of possible words that this code generates and see which one is the closest. So for example, if I had actually sent 1, 0, 0, when I run this through the code matrix, I get 1, 0, 0 on the next 3 bits as well when I do my multiplications through there. Well, see, here, if that's true, then I would have made 2-bit errors. In most communication systems, 2-bit errors is much less likely than 1-bit error for a short block like this. And therefore, the more reasonable interpretation is that I've sent this code word, which is the only one that has 1-bit difference separating between here and here. So the scheme for block codes is very simple. The decoders can actually be very complicated because it turns out that it's not so much the redundancy in any error correction code, block or otherwise, so much as the complexity that buys you the ability to recover your bits. And you can probably see that if you think about it in this terms. What happens if I just had like the identity matrix here? This is the world's lousiest. Well, this isn't even an error correction scheme. This is an error detection. Because what I'm really doing is I'm just repeating the first 3 bits. Well, OK, now I make a bit error. Oh, yeah, this bit doesn't agree with this bit. Well, which one was it? Maybe I need a 3rd identity matrix so I can vote, right? I transmit the thing 3 times, and I'll let the best 2 or 3 determine. Well, that starts to get extremely inefficient. Extremely inefficient. Rather, it's better to build in complexity because it eliminates the need to vote. The bigger your code matrix gets, the more reliable the actual code becomes. Let me show you a graph out of your book. This is a great illustration of what I'm talking to. Let's switch to the overhead again. Turn this on. Got some permanent marker stains on here, but I think you'll still be able to read it here. OK, look what we have here. Here is uncoded BPSK. We've got EB over N0, which we know is proportional to signal-to-noise ratio. in dB along this axis, and probability of bit error, 10 to the minus 2, 10 to the minus 4, 10 to the minus 6, 10 to the minus 8 in the vertical axis. So it's just the same plot that we derived in class, just recast in a different scale, in the dB horizontal scale. Even more, you can see that you get a terrible, terrible performance, and then the bit error rate falls off the table. And anything beyond 10 dB, you're actually getting into pretty reliable transmission, past 10 to the minus 8, 1 bit per million. Okay, that's uncoded binary phase shift keying. BCH, that's a type of block code. In fact, it is a 127/64, a rate 64 over 127. So it's almost 2-to-1 redundancy. I'm adding twice as many bits in my coded bit stream as I do in my data bit stream. Okay, that's nice. Look at that. It falls off the table even more. You basically, anything above 7 dB, and this is almost perfect transmission without error. If I drop below 7 dB, I can't use it. It's unusable. And there's a pretty significant gap between these that represents my coding gain. I can now, I mean, look at that, just on here, for the same reliability level, 10 to the minus 6, 10 to the minus 7, I'm getting like 5 dB of difference between those curves at that point. That's 5 dB that you could back off your transmit power or use to increase your signal length, move your satellite to a farther Earth orbit. That buys you a lot, this block code. And it's really just rearranging ones and zeros, which we can do with extremely low power levels nowadays and cheap hardware. Now, look at this. Here's another form of BCH code. This one's even more complicated. You put 688 bits in, and you get 1,023 bits out. So it's a lot bigger. The generator matrix is a lot bigger than this little 64/127. Interestingly, though, there's less redundancy. The ratio of 688 to 1,023, that's only about 2 to 3. So there's less redundancy, but much more complexity. And look, the curve is actually to the left. You added about 2 dB of operation, switching from this less redundant but more complicated code. So really, it's the complexity, not the redundancy, that's buying you something in these systems. Now, there's another scheme of coding, convolutional code. Rate 1/2 convolutional code, soft decision, k equals 7. I'll mention about what those mean in a second. But that even outperforms these BCH block codes. And then here, this is actually a coding scheme. This little line that just goes, it's operating close to 0 dB. So that's actually close to what the Shannon channel capacity theorem would predict for this. By what means of magic is it operating at? This is a rate 1/2 turbo code. Turbo codes were invented about 20 years ago by some French scientists, and they did a marvelous job. For the first time, it allowed communications engineers to achieve something close to the Shannon channel capacity. I'll mention briefly how they work in a moment. But I just wanted to show you this to emphasize that these codes buy you quite a bit of margin in a communication link, and it's the complexity, not necessarily the redundancy, that buys you that gain. Okay. Now, different types of block codes that you'll see in practice. The ones that we saw on the board, the BCHs. BCH actually stands for the inventors who were Bose, Chowdhury, and Hockenham. Nobody ever calls it the Bose-Chowdhury-Hockenham code. It's the BCH code. They came up with a rule for generalizing the construction of these generator matrices for certain types of codes. And that's used commonly. The Reed-Solomon, you may have heard this. This is used in satellite links. This is also used in compact disc recordings, CDs. Golay codes, you may have heard this. And there are lots more, but these are some of the common ones that you'll see built into the standard. Uh-oh. My apologies. Everything from now on is going to be in red. You knew exactly what happened. Thank you. Appreciate it. That is a design flaw. And it has not happened to just me, apparently. There's all sorts of erasers and markers down here. Fascinating. Okay. Now, that's block codes. You slice up your data stream into well-defined lengths of bits, and then you code them into larger but still well-defined lengths of bits. There's another form of code, error correction code, called a convolutional code. The convolutional code, here's an example of a convolutional code. You take a data stream and you run it through a shift register. So what does a shift register do? It takes even clock pulses, and every time it gets a clock pulse, it moves the data over. So the input, in this case, is 0. It moves that into this register and holds it. And then when it gets another clock pulse, it moves this over to the right and then takes the next data bit, et cetera, et cetera. Usually initialized to 0 initially. So you take this, let's say, as an example, you sum up all the bits in the shift register. So here I've got three registers, and I add them up. And then over here, maybe I just add the first and the last. I take that result. And then I take this switch and I sort of double time it. I get the top and the bottom each clock cycle. Top, bottom, top, bottom, top, bottom, as I move things along. So what would this look like? Well, if I put in, let's do this data stream, 0, 1, 0, 1. So here's 1 is going to pop in, then 0, then 1, then 0. That will initialize everything to 0 to start with. What does the output stream look like? Well, I get my first state has 1, 0, 0 in it. I add 1 to 0 and 0. I add 1 to 0. I'm going to get 1, 1 on the output. I shift everything over. Now I get 1 on my top, 0 on my bottom. I shift everything over. I get 0 on my top and 0 on my bottom. I shift everything over again. I get 1 on my top, 0 on my bottom. So you get the point. We would call this a rate 1/2 convolutional encoder with constraint length of 3. The constraint length is the number of shift registers, or the sampling over time of your bits that you're folding into your calculation. And you let this thing run continually. So it doesn't really matter what size your input data is. It works on an infinite-sized input data. And you can see that your output doesn't necessarily resemble your input because this is getting folded into here. You can have rate 1/3 convolutional encoders. That's really a measure of your redundancy, that first metric. The constraint length is a measure of your complexity. And so, as I said earlier, it's really the constraint length that buys you the most ability to correct bits. How do you correct the bits at your receiver? What algorithm do you use on a convolutional encoder? Use something called the Viterbi algorithm. It's this algorithm that basically looks at your sequence, and even if there's errors in there, it's doing essentially what you did in your head when you read the sentence. It plows through the modulation, the decoded points, and tries to measure the distance closest to the most realistic track through the data that's allowable by the code book. And then it snaps to that track, thereby correcting any errors that you've made along the way. It's computationally intensive. You've got to kind of go through it several passes in order to find that track. But the algorithm that allows you to do that is the Viterbi algorithm. You probably learn it in your digital communications class if you take a class in that. We don't have time to cover it, but that's basically how it works. And, of course, it gets more complicated the higher your constraint length. There are no... We used a convolutional encoder in the 2G cellular standard, and that had a constraint length of 9, so this would have been in the mid-90s. That would be top of the line. We would have had trouble building anything that could decode beyond a constraint length 9 convolutional decoder. In fact, there's a story, I don't know which NASA mission this was, but there was a space mission that was sent to a planet. And of course, it takes several years to get to an outer planet, especially. And they, it was a long-distance link. You really need all the dBs and the coding gains if you want to transmit data on a deep space link. So they launched the spacecraft with the convolutional encoder of a constraint length that they hadn't built yet. In fact, they couldn't build it yet because it was too complicated. They had to wait for Moore's law to catch up with it. But they said, well, 4 or 5 years we'll be able to do it. And so the encoder is actually very easy to build. It's just shift registers and some simple arithmetic operations. The decoder is where all the computation happens. This is where all the complexity is, trying to work through all the possible states of your convolutionally encoded signal. So you just let Moore's law take care of it, though, because at the end of the day, it's all ones and zeros. If you have a nice algorithm, you just wait enough time, and somebody will invent a processor that can handle it. It's pretty predictable. Now, one last comment before we leave coding theory, because you do need to know how this operates. The turbo code is based on a convolutional encoder. What you do is you take 2 convolutional encoders, so you take a data stream, you pass it on through. So out of this line, you get raw data. Then you take that same data and you run it through a convolutional encoder. And it comes out this line. We'll call this point x sub k, y1 of k, and y2 of k. Then you take the data and you interleave it. That's what this INT block is. Interleave just means you take the bits and you rearrange them in order. And you run it through another convolutional encoder. So now you've got 3 data streams. You're already talking about rate 1/3 if you transmit all of them, so it's a lot of redundancy. However, when you transmit them, you can decode this with almost perfect reliability, close to the Shannon channel capacity level. Remember, it's the complexity, not the redundancy, that's buying you something. So in fact, in some turbo codes, you don't even transmit all these. You throw away values. That's called puncturing in coding theory. When your code is so good, you can actually throw away bits. And this helps you to reduce the coded bit rate and fit your signal in a bandwidth without losing too much on your actual code. So there's this theory in coding theory called, and we offer several classes on coding theory, I think here at the graduate level at Georgia Tech. But there's a saying that says, all codes are actually good codes that are probably getting pretty close to the Shannon channel capacity. The only bad codes are the ones we can think of, right? The only way to make a code that we know how to is to codify it in some sort of simple algorithm that can be executed by a machine. If you just find a way to make a random code, like a huge code book with sort of random codes, it actually turns out to be a really good way to code. But we don't have any way to decode that easily. You can't make a table lookout up for some of these things because it's just too complicated. And so this is a way to artificially make it look like you're constructing a very complicated code. Data bit, convolutionally encoded bit, completely different convolutionally encoded bit. What does the decoder look like in this? Well, you need something called an iterative decoder to figure this out, but it can be done with an algorithm. So the decoder, you take your x values, you take your y values, even if they're punctured. So the operation principle is actually very simple. You've got a series of xk's and yk's, your data bits and your convolved data bits, both the convolutional encoder output 1, convolutional encoder output 2. Even if they're punctured, even if you've actually thrown data away, you put your raw data bits in here and your first set of y's, the output of the first convolutional encoder here, and you perform a Viterbi algorithm to try to decode them. You come up with the best possible estimate of x of k, and then you feed that into an interleaver, and you repeat the exercise with decoder number 2. Try to decode what was coming in through here, along with your new estimates for x of k, your actual data. Now you've got a better estimate of x of k. You feed that back through the system, and you re-decode your system again and again and again and again. So I believe that graph that I showed from your book, the one with the turbo code plot, that was actually, I think it took 19 or 17 iterations of this cycle. Actually, this is why they call it a turbo code, because it's like the repeated cycle of a turbo engine. When the modulation scheme gets complicated enough, it's actually very difficult to get any sort of semblance of an analytic solution for your bit error rate curves. You almost always have to resort to simulation. And your simulation is going to depend on how many iterations you've done of this coding. The only way that they were able to get that steep curve is if they'd iterated 19 or 17 times. But this is a type of scheme that's come about in the last maybe 15 to 20 years in digital communications that allows you to get to the Shannon channel capacity theorem. People have found out that this is really kind of a special class of a low-density parity check, LDPC code, which is also has gained favor in communications recently as another class of codes that can get you very close to the Shannon channel capacity theorem.